So now we are in the realm of starting the process of looking at geometric optics. Now, even though we're still in chapter 33, where we introduced the basic idea of what is light as wave, second half of 33 does geometric optics. So second half of 33 and then all of 34 do geometric optics. So really this is a topic that really ought to be in the next section. But we start off with reflection and then refraction. Now, reflection, we have actually, we're going to concentrate on what we call specular reflection. So specular reflection. For specular reflection, if we have parallel waves of light coming in, they bounce off of a smooth surface that's parallel. There's also diffuse reflection where light hitting a rough surface comes out in different directions. We're not going to worry about diffuse reflection, so we're just going to do specular reflection. The basic idea of reflection is if you got a smooth surface, if you draw a normal to the surface, then light coming in reflects at the same angle that it came in at. So we measure the angle relative to the normal. So we have the incidence angle and the reflective. So we would say the angle of incidence equals the angle of reflection. And so this is our basic idea of reflection. Okay, so with that, we'll do a couple of examples of that, but I'm going to go ahead and talk a little bit about refraction. Because that's our next idea here is what if light refracts? In lab, we've already introduced the idea that speed of light could be different in a medium. We've talked about it here too. We've said, for example, that if you have a material here and light's traveling through the material, the speed of light in a vacuum is going to be 1 over square root mu naught epsilon naught. The speed of light in the material is going to be 1 over square root mu epsilon, where epsilon is actually going to be, this is going to be 1 over square root of the magnetization mu naught and the dielectric constant epsilon naught. So that means this is always going to be less than the speed of light because k and m are always going to be greater than or equal to 1. And so the ratio speed of light to the speed of light in the material we call the index of refraction, N. Now, we have a material called N1, another material N2. Now, I'm just going to make an assumption here, for example, that N2 is greater than N1. It doesn't have to be, but for this example. So that means if I have light rays coming in like that, okay, so I got beams of light coming in like that, and we know the light is waves, so if I draw a line for the wave front, so the top of each wave, okay, here, likewise here and here, but the light doesn't travel as fast in here. So in the time that it takes light to travel from here to here, it only traveled a little bit here. And so that means this is going to be bent like that. And so here it only travels a little bit, and here it travels more over here. And so what happens is that if these lines are perpendicular to the wave fronts, lines here perpendicular to the wave fronts are going to be a different angle. So we can call this theta 1 and call that theta 2. And so what happens is that clearly light appears to bend. A beam of light or ray of light appears to bend in the material. So let me zoom in to this little area right there. So what we've got is, we've got the surface. Okay, we've got the normal to the surface. We have some light that comes in here. You know, another parallel beam is right here. They appear to bend right here. So this is theta 1 and this is theta 2. So if I draw a perpendicular right there, that's perpendicular, and then here I draw a perpendicular right there. Okay, so if this is theta 2, then this is also theta 2. If that's theta 1, then this has to be theta 1. Now, you think about, well, why is that the case? Well, that's got to be the case because, you know, this angle right here plus theta 1 is 90 degrees, but it's also this angle plus this other angle is 90 degrees. So those two this angle and this angle had to be theta 1, like the same argument for the other side. Okay, so now we look at it and we say, well, if we look at it, you know, we can call this distance right here d2, and that distance d1, and then this distance right there is L. And so we would say that sine theta 1 is going to be equal to d1 over L. Likewise, sine theta 2 equals d2 over L. Okay, so with that, we know that L equals d1 over sine theta 1. It's also equal to d2 over sine theta 2. So d1 over sine theta 1 equals d2 sine theta 2. Well, then we look at it and we say, well, d1 is the distance that the light traveled in the material, in material in 1. And d2 is the distance that light traveled in the material in 2. And so distance in the same length of time, they travel different distances. And so that means that d1 is the speed of light in material 1. That's going to be speed of light over n1 times time. And then d2 is speed of light over n2 times the same time. Okay, so we can plug that into the expression that we just had right there. Okay, so we could then say that c over n1 t divided by sine theta equals c over n2t divided by sine theta 2. So the t's cancel, the c's cancel. We can cross multiply here, and so we would see here, you know, this is 1, 1. So basically that means n1 sine theta 1 equals n2 sine theta 2. So putting that again, n1 sine theta 1 equals n2 sine theta 2. Okay, that is what we call the Snell-Descartes law, or sometimes it's just called Snell's law. Kind of missing out on what Descartes did with it, but that is our basic relationship for refraction.